Hello! 10.1 is entitled Energy and Work. There's a few definitions that we have to get through just to talk about work and energy. But before we do, I wanted to watch a quick video that I found very interesting dealing with energy.
Energy is all around us, a physical quantity that follows precise natural laws. Our universe has a finite amount of it. It's neither created nor destroyed, but can take different forms, such as kinetic or potential energy, with different properties and formulas to remember. For instance, an LED desk lamp's 6-watt bulb transfers 6 joules of light energy per second. But let's jump back up into space to look at our planet, its systems, and their energy flow. Earth's physical systems include the atmosphere, hydrosphere, lithosphere, and biosphere. Energy moves in and out of these systems, and during any energy transfer between them, some is lost to the surroundings as heat, light, sound, vibration, or movement. Our planet's energy comes from internal and external sources. Geothermal energy from radioactive isotopes and rotational energy from the spinning of the Earth are internal sources of energy, while the sun is the major external source, driving certain systems like our weather and climate. Sunlight warms the surface and atmosphere in varying amounts, and this causes convection, producing winds and influencing ocean currents. Infrared radiation, radiating out from the warmed surface of the Earth, gets trapped by greenhouse gases and further affects the energy flow. The sun is also the major source of energy for organisms. Plants, algae, and cyanobacteria use sunlight to produce organic matter from carbon dioxide and water, powering the biosphere's food chains. We release this food energy using chemical reactions, like combustion and respiration. At each level in a food chain, some energy is stored in newly made chemical structures, but most is lost to the surroundings as heat, like your body heat, released by your digestion of food. Now, as plants are eaten by primary consumers, only about 10% of their total energy is passed on to the next level. Since energy can only flow in one direction in a food chain, from producers onto consumers and decomposers, an organism that eats lower on the food chain is more efficient than one higher up. So eating producers is the most efficient level at which an animal can get its energy. But without continual input of energy to those producers, mostly from sunlight, life on Earth as we know it would cease to exist. We humans, of course, spend our energy doing a lot of things besides eating. We travel, we build, we power all sorts of technology. To do all this, we use sources like fossil fuels, coal, oil, and natural gas, which contain energy that plants captured from sunlight long ago and stored in the form of carbon. When we burn fossil fuels in power plants, we release this stored energy to generate electricity. To generate electricity, heat from burning fossil fuels is used to power turbines that rotate magnets, which in turn create magnetic field changes relative to a coil of wire, causing electrons to be induced to flow in the wire. Modern civilization depends on our ability to keep powering that flow of electrons. Fortunately, we aren't limited to burning non-renewable fossil fuels to generate electricity. Electrons can also be induced to flow by direct interaction with light particles, which is how a solar cell operates. Other renewable energy sources, such as wind, water, geothermal, and biofuels, can also be used to generate electricity. Global demand for energy is increasing, but the planet has limited energy resources to access through a complex energy infrastructure. As populations rise alongside rates of industrialization and development, our energy decisions grow more and more important. Access to energy impacts health, education, political power, and socioeconomic status. If we improve our energy efficiency, we can use our natural resources more responsibly and improve quality of life for everyone.
So that was just kind of an introduction to energy. You know, you've heard energy can neither be created nor destroyed, that energy the universe has a finite amount of it. We take in energy, we give off energy. Energy, neither you don't make it, we don't create it. It's just always transferring from one form to another. So the first thing that I want to define today is work. Work in the physics sense is a force times a distance. Now you have to exert that force in the direction of motion. Force times distance. Power is the time rate of work. Meaning that if you do more work divided by less time gives you more power. Or you do more work in that same amount of time, more power. Kinetic energy. Kinetic energy is the energy of something that has motion, the energy of motion. That's 1/2 times its mass times its velocity squared. And then lastly, the work energy theorem. Work is equal to the change in kinetic energy. Whenever we do work on something, we can influence and change its kinetic energy. For instance, if you push on something for a certain amount of time or distance, that's work, you will make it go faster. Kinetic energy. Very simple. The first thing here, working or not working. For instance, if you push on something like a box against the floor, yes, we are doing work. What if you're just walking across the floor? The floor is exerting a force up on us, but we walk across. No, we're not doing work. The force has to be in the direction of motion right here. What if you lifted a bag of groceries? We're exerting a force up, it's traveling up. That means that yes, there is work done on this. What if we carry groceries across the floor? We're lifting, but we're traveling perpendicular to that. No, we're not actually doing work in this case. Now, I have another couple of pictures here. If you're pushing on something and it doesn't move, you're doing no work. Even though you're exerting a force, that doesn't mean that you're doing work. Here you are, you're like being pulled by a ski rope. Yes, there's a force pulling you times the amount of distance that it takes. That boat is doing work on you. And then lastly, what if you're pushing at an angle? Now we only use if this is the direction of the force right here, we're only going to use the component of the force in the direction of motion. So we take this force right here, this component times this distance to figure out our work. Again, this is another picture from your book. It talks about if you slide this across the table, gravity's pulling down, the table is supporting it, and you're pushing it that way. There's no work done on it because the forces that are at play here are up and down, and then you're pushing it left and right. Same with a planet orbiting the sun. It's traveling in this direction, but the force is in that direction, so there's no work done when things orbit either. I found this really interesting infographic about work, energy, and power that I'll just leave you to read through on your own, but I wanted to go through a couple of example problems for you in dealing with work, energy, and power. So here's our first one. It says, a 105-gram hockey puck is sliding across the ice. A player exerts a constant 450 newtons of force for this distance. How much work does the player do on the puck? So here's my puck. Work is force times distance. Now it's the force I'm exerting. This is the force I'm exerting, 4.50 newtons in the direction of motion. So I'm pushing in a distance of 0.150. Now, again, there's a lot of forces at work here. There's the force of gravity, which is 0.105 times 9.8. And then there's a normal force here. And then we're also pushing it with some push. So this is the only force we work with when we're dealing with work because it's in the direction of motion. These other two are not. So if I take 4.50 and I multiply by, let's turn, so 4.5 times 0.15. This is 0.675. Now, that's going to mean Newton meters. Or another unit that we have for this is a joule. And you saw that in that video, that 1 watt is equal to a joule per second, and this is a joule. A joule is a Newton meter. It's a unit of energy. Now, my next question says a sailor's pulls a boat a distance of this along a dock. So here's my boat. I'm pulling it with this force at an angle of 25 degrees. So this is 25 degrees. I'm pulling it 30 meters. With a force of 255 newtons. How much work does the sailor do? Now again, work is your force times your distance. Now it's not just the 255 is not the force that's going to go in here. We're going to have to find the force in the direction of motion. So what I'm going to end up having to do is using a little bit of trigonometry here to figure out the force. So it's going to be this right here. We'll call this the force parallel. So we'll use cosine. We'll say the cosine of 25 degrees is equal to the force parallel divided by the hypotenuse, which is 255. So if I take 255 times the cosine of 25, I've got to make sure my calculator again is in, now it's in degree mode. So let's make sure it's in degrees. It is 255 times the cosine of 25. So 231. So this force is 231 times the distance of 30 meters. So I take 231 times 30, and I get 6,900 or 6,930 joules. And the third example problem. An electric motor lifts an elevator um, 9 meters in 1.5 seconds, 15 seconds by exerting an upward force of this many newtons. So here's my force. 1, 2, so 1, 2, 3, 4, 12,000 newtons. The distance that is exerting it is 15, I don't know, 9 meters. And the time that it takes is 15 seconds. So I'm looking for power. Now, power, if you notice back to that first slide that I had up here, power is work divided by time. So this is the equation that I'm going to be doing, I'm going to be utilizing here. So it's the work divided by time, or force times distance divided by time. So again, my force of 12,000 newtons going to multiply by distance, 9 meters, divided by my time of 15 seconds, it comes out to be 12,000 times 9 divided by 15. 7,200. Now, my units could be Newton meters per second. We also learned in the last couple slides that I could also write it, because a Newton meter is a joule, so this could be joule seconds, but also a joule second is equal to a watt. So this could be 7,200 watts. A lot of crazy stuff going on with units. So just to kind of give you a quick overview of everything. 1 Newton, a Newton is a kilogram meter per second. A Newton meter is equal to 1 joule. A joule per second is equal to 1 watt. These are kind of things that, I mean, I just take for granted because I know and use them, but maybe you don't, and maybe you want to write those down. So this kind of concludes energy and work. Energy being pushes our what we use, we consume it. It's tough to define energy and work.